So as I was saying the other time, I said the number of reactions or pin reaction inside this thing, we have two. We have to, because it's just a single pin here. Now, if we have another pin here, that means we have four. So for this particular, our Fy is equal to 2. Now, if you do the calculation using that equation, we have 5 is 5 plus R plus Fi, 5 plus 2, maybe it's greater than or equals to 2, equals to 3n. So our member is 1, 2, 1, 2. Now, if we have two members, by the time we equate it, we have 7 is greater than 6. So it is indeterminate to the first degree because the difference between the two is 1. Let me move to other. I think that's all on this one. So I will give us an example that we'll just do after. You people can try practice this particular one and let me see what you have later. You can do it and show me later.
Yes.
Let me go to trusses. Now, in a truss, we have what we call the support reactions or the support, and we have the joints. And if I say joints, we are talking about all these points for joints. The reaction, depending on what we have here, if it is pin or fixed or whatever it is. But the member from here to here, this is a single member, this another member, this another member, like this. That's how we resolve a truss member. So you can read all those theory later. Let me just Now look, using this particular one, it says that to determine the determinacy and stability of this structure, we have to control them like a triangle, like this. Then we are going to use I plus R is less than 2J. Now, what is I? What is R? What is J? I and J is equal to the number of joints. I is the total number of links, and R is the minimum number of reactions required for the determinacy. Let me go to an example. Let me just go to an example. Now, let's say we have this example that you have. Okay. In this particular one, assume that we have 3 unknown reactions, a pin and a roller. Let's say that we have a pin here and a roller here. That let's resolve this one. Now, this particular one, how many number of joints do we have? We are supposed to have 1, 2, 3, 4, 5, 6, 7. 7 joints. But how many I do we have? We said I is what? I is the total number of links.
Then
now you can see the way we mentioned the I. 1, 2, 3, 4. That is like the number of members, and then our I is 11. So if you use that equation, I plus R equals to 2J. I 11 plus 3 equals to 2 times this. That means 14 plus 2 times 7, 14. So that means it is stable, and it is let me say it is determinate. But if it is greater than or less than, you know what? If it is greater than, it is indeterminate. If it is less than, it is unstable. Now, let's look at this. In this particular one, I've numbered them already. We have 15 members altogether. 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 joints. How many reactions? Let's say we have a pin and a roller support. We have 2 plus 1, that's 3. Please, I said assume we have 2 unknown reactions, a pin and a roller support. This clause, that's why because I didn't show it in this diagram, that one try to explain to us here. So if you apply that principle, you also determine whether it is stable or it's indeterminate. You can use that method for all these ones, but this particular one here, this one here, I want us to look at. Okay, let's look at this. I love these members. This particular one here, we have member 1, we have member 2, we have member 3, we have member 4, 5, 6, 7, 8, 9, and 10. But if you are not careful enough, somebody can be looking at this and say, maybe I will say this is 1, this is 2, this is 3. You have to be careful. This is one member, this is another member. You have to be careful so that you don't miss it up. This one, how many members do we have here? That's the number of members we have here.
1, 2, 3, 4,
Are you
5,
ready?
6, 7, 8.
9.
It's not 8 though.
9 now.
It's 9 members.
Okay.
Now.
We have 1, 2, 3, 4, 5, 6, 7,
12, 12,
8,
12,
and 9.
12 members.
9.
No. All these members, they cross like this one cross like this one cross like this. That's 3 here.
Yeah,
Yeah, from here to here is 4, from here to here is 5, from here to here is 6, from here to here is 7, from here to here is 8, from here to here is 9. That's why we have 9 members. But reactions, we have 2 here, we have 1 here. That's why we have 3. But the number of joints, that's 1, 2, 3, 4, 5, 6. Number of joints is 6. So it's very simple but tricky if you don't look at it very well. So let us look at want to do we have actually I shouldn't waste time on this. I believe everybody can be able to do that one. Let's look at this particular member. I believe people can resolve this particular member if you see this member. Can you resolve it? Can you calculate the reaction at A, reaction at C, and everything? I believe you have done it before now. Okay, let's look at this member. It is very easy when you have a member like this to resolve it is very easy. Now, the main thing is that you have to have understanding of the kind of support condition is having. That will determine the number of reactions you are looking for there. For this particular one, we have 3 unknown reactions because it's fixed. And for this one, we have 1 unknown reaction. However, there's a moment that is applied in this place also. So you have to take it into consideration. Now, where we have a pin support, we know that, okay, that member, they say, that member is having 2 unknown reactions in that place, which we will determine. Now, when you have a uniformly distributed load, you all know your uniformly distributed load. This uniformly distributed load, it says 6 kilonewton per meter. That is, for every meter, the force applied is 6. So if we have 6 meters, that means the whole total number of load will be 36. Am I too fast? This is 6 kilonewton per meter. So what it means is that for every meter, the 6 kilonewton that is applicable. Now, when we have a uniformly distributed load like this, that spans like this, if we want to convert it to a point load, all we just need to do is multiply this one by the span. That would be 6 times 6, that's 36. So that means the 36 will be acting at the center here. So that means the 36 will be acting at the centroid here. And okay, yeah, okay, so yeah, 36 will be acting at the center here. Because somebody might be asking me, how did I get this? And the other time I explained that we have fixed support. That means we are supposed to expect 3 or no reaction here, which we are seeing forces along the S, forces along the Y, and the moment. Y for this one, we have inch. So it's 2 that's for the inch. But there's one thing about inch. When we have an inch support, the if we have this one coming like this at this other end of this member, the other end of the member, it will be going the other direction. If this one is coming like this, at the other end, that will be going the other direction. I hope you understand. That's the principle of how we, this is the principle of how we analyze a shear at a particular member. And in this particular one, I think it's, let me just look at this example. Okay. Now, if I want to get, let's say I have a force here. I want to get the force at this other end. Or let me say, okay, normally we are looking for AY, AS, and MA. Then we're looking for, at this place, we're looking for CY. Now, if I want to get this CY, what I will do is that I will take moment about this particular joint. If I take moment about these points to be 0, what it means is that everything here will be 0, then I'll be left with just the force times perpendicular distance here to create a moment. You know what? In this case, in this case, in this case now, we want to take moment about B to be equal to 0. Why are we doing that? Because there's a hinge here. Just like the member I illustrated for us the other time. It can bend in that particular form there. So we have to treat them separately because of that hinge. What can happen in that place? It can't be like a normal single ruler that you're having. The way I bent that one the other time. So we have to take it one by one. So if we are taking moment about this point here, this point B, what it means is that if I take moment about this point B, I will not say, okay, since I'm taking moment about point B, I will now resolve force times perpendicular distance to this particular place. So that means every other thing here will be negated at 0 first when I'm taking the moment about that place. So we said summation of moment about B to be equal to 0. However, there's something we call sign convention. This sign convention, what we're trying to say is that if I am moving in clockwise direction to resolve a particular problem, I have to make sure, okay, if I say clockwise direction is positive, that particular direction is what I must maintain till I finish my calculation. I cannot change it in between. That is, if I move in the clockwise direction is positive, that is the principle that we use till I finish solving that particular problem. If I'm going in the anti-clockwise, I have to use negative. If I say positive, clockwise is positive, anti-clockwise is negative, I have to maintain that principle. And that is why we always put this sign here. When I say summation of moment about B to be equal to 0, in what direction are you following? So in this one, what I'm saying here is that if I move in this direction of this arrow, in this anti-clockwise direction, I'm saying it is positive. Are you getting me now? So if I have established this, now I'm taking moment about B to be equal to 0. What I will do is I will not take all these force. I will sub them towards this particular point. Mind you, moment is force times perpendicular distance. Since moment is force times perpendicular distance, we start with this one first. AS, does he have any perpendicular distance that you travel to this particular place? No. AS times 0?
No.
Now, this moment is not having any value here. We treat it at 0 for this. Now, the other one we have is AY. This AY that we're having here, this AY, it must travel a distance of force times perpendicular distance, which is 6. Force times perpendicular distance, which is 6, to get to this place. Now, I think I need to, let me put this on board. Let me put it on board. Can I share my screen? Let me see whether you can see my screen. Share. Wait. Where's my camera? Let me put this one on board. This camera is not clear. The camera is not clear, Abi?
Yeah, it's very dark.
Okay, let me see possibility of turning with another camera. Let's give it a few minutes. This one.
Josiah.
Sir.
I'm with you. I don't know what that is.
Okay, it's clear now. It's clear now.
Can you see this
Can you
screen?
see this screen now?
You can see, but it's far away from us. Family is not very clear.
Okay. Sorry,
I
don't know.
don't know.
And it's
Need and it's already.
So
So
let's say I
let's
have.
say I have.
Can you see this
Can you
screen?
see this screen?
Can see, but not very clear.
But what?
But what?
From us.
Eh?
Eh? Let me read it. Let me just know this.
You can see clearly.
Okay, thank you. Now, I have this member like this. And let's say we have this way. This is that's our UDL. This is meters. This 4 meters. Member B, A, and C. Now, I talk about sign convention. If I am moving like this, I have to establish whether it is positive Hello.
Yeah, we can hear you, sir.
Okay. So I have to establish whether moving in this direction is positive or it is negative. Anyone you choose is left for you. But in this example, what we did is that we said let this direction be positive. This is positive. It is very important for you to indicate this so that everybody will be able to understand what you are doing. Now, if I say this is positive, that means this direction is negative. Using this principle is what we're going to use in solving this problem. Now, in this particular instance, we have member A to B and B to C. Let us look at member A, sorry, I didn't understand. Member A to B. Member A to B. Then I can be talking about B to C. Now, in this member A to B, if we want to solve it, we have to take moment to a particular point. For instance, the one we have in this place, in this member A to B, we said, let us take summation of moments about member A to be equal to 0. And then we adopted this sign convention. This is positive. So let us look at this member A to B now. We want to look at what we're going to have. Where are we taking moment to? We are taking moment to this particular point. And after breaking it down the other time, we said our disjointed member is this, that the one coming here is our AY. I'm blocking the camera. Okay. We said the one coming here is AS. And then because it's a fit, there is a moment moving like this. Now, I explained to us also that because this place is pinned, we must have two or no reaction there. And I said when we have it like this here, and the other member B to C, it will not be like this and like this. That it has to be opposite of what we have here, so that we have a balanced member. Now, treating this member A to B, we are taking moments about this place to be equal to 0. Mind you, this point B, so we have B along the y-axis and B along the x-axis.
Mute your mic, mute your mic, go. It's echoing.
Let me mute up. Oh. Sorry, I can't mute up because
Sir, he's not referring to you, sir. He's not referring to you to mute your mic. His others, our colleagues, they should mute their mic, not you, sir.
Not you, sir. I mean,
I am trying to mute others. Hello? Okay, better now. So as I was saying, if you are taking moments about point A, careful. Hello?
Yeah, yeah.
Yeah. So we are going to take a moment about point A to be equal to 0, as I've explained here. If we are doing that, what it means is that the forces in this point B are the ones that we're going to resolve to this place. That is, all the forces in point A will not take effect because we are taking moment to that particular point A. So what it means is that dy times this perpendicular distance has to take place. But there's something I want us to look at. There's a uniformly distributed load here, which we must convert to a point load before we start our calculation. How do we go about that? Since we said it's 6 kilonewton per meter, that is every meter it is 6. To convert this to a point load now, it's going to be 6 times 6, which is 36, and then it will now act at the center. So we have 36 kilonewton here now. For this, because of this uniformly distributed load here. Now,
Observation, sir.
okay, I'm with you.
Observation, sir.
Okay.
Thank you, sir. Yeah, we can only see your picture. We can no longer see the
Okay, you can see the camera again.
the no, Marcus body. Yes, sir.
Sorry. Let me. Sorry, my picture. Is it showing?
No, no, sir.
You can't see my camera. It's showing now.
It's already showing your picture, sir. Okay, it's showing now. It's okay.
It's showing now, sir.
Okay. Now, what I'm saying is that since we are taking a moment about this point, all these forces here will not take effect. The forces here, because if you say this force times perpendicular distance, because it's at this point, the perpendicular distance is 0. So the forces and the forces along the x and the y axis here will not take effect. But had it been that we have a moment here that maybe it's something like 6 kilonewton or whatever it is, it's going to take effect. Are you getting me? Now, looking at this, I want to resolve this. And if I take force times perpendicular distance, but there's a moment here which we don't know the value. What it means is that I should not start my calculation from this end. If I start my calculation from here, I will not know the moment along this place. That one will seem like unknown. Or let us try it. Let's try it. So if I say I want to resolve this one now, this force times perpendicular distance, because this one is along this axis, it does not have any perpendicular distance up or down. So ds is out of it. But dy times what perpendicular distance is going to travel to this place? Force times perpendicular distance, 6. Now, if it's going to move to this side, it will move in this direction. Right? It will move in this direction, right? From here to here. But what is in my sign convention? In my sign convention, I said whatever is moving like this is positive. So this one is positive. So I take this one as positive. It's positive this way. Now, it continues to move like this until it gets to this place. But as it's moving, there's another force here acting downward. This 36 kilonewton is going to apply a moment to this place through this particular distance. And since it's acting at the centroid, so from here to here is 3 meters. 3, right? From here to here is 3. 3 meters. So if I'm coming like this now, I have 36. 36 times 3. However, is it positive or negative? Let us look at if somebody is coming like this, how will you get to this particular point?
Hello, sir.
Right?
Hello, sir. Hello, sir.
I'm with you.
That 36 kilonewton, I know from the onset it was a uniformly distributed load, 6 kilonewton per meter.
Yes.
Does it mean that 6 was used to multiply the 6 meter?
Yes.
To rule out the meter to get 36 as point load?
By the time we multiply, it's uniformly diluted load. If you convert it to a point load, you have to multiply by that span of that particular load. So, and
okay,
the
sir.
span is 6 meters. So 6 times 6 is 36. That's why we have 36 there. But when you do that,
okay,
that
I've got it now. Thank you, sir.
It's divided at the center of the member. So if it's coming, it comes like this, in this direction. Now, if I look at my sign convention, if I have this one, is it positive or negative? This direction, is it positive or negative?
It depends. If they've got anti-clockwise, it's negative, but clockwise is positive.
Initial sign convention that we say we are using. That anything coming like this is positive. So if I have something like this in between, what is it positive or negative?
Negative. Negative.
Very good. So that way we have minus 36 kilonewton times 3. So do you have any other force to this place again? No. So which equal to 0. Because we get summation moment about 8 equal to 0. So this is what we are going to treat. Now, here we have 6by to be equal to 36 times 3. That's what 36 times 3?
That should be 100 and
108.
Oh, yeah, we use my calculator. 108.
108.
Is 108.
It's on 108. So by equals to what? 108 divided by 6 is equal to 18 kilonewton. So that's my by. So, but however, let me look at what did I do here? What did I do? Sorry. Okay, I know. Okay, as I explained the other time, they are looking at this. I've forgotten that we are trying to explain something the other time. You know, I told us the other time that if we are taking forces along this place to be equal to 0, because we are taking moment about this place to 0 rather. But I said something the other. I said there's a moment here that we don't know. That this moment that we don't know, that if we start from here, we are going to have a problem. And I tried to just show us how we might have a problem. But I now forgot. I'm believing I'm doing the calculation on. So if I'm taking it this way, this moment, I don't have how to resolve it because the value is not known. And we don't equate a moment to 0 if we don't, we have to calculate it out. I think this is a roller support or a pin support. There won't be movement. What I've done here would have been